Hi and welcome to another very exciting tutorial in our 24 Days of Swift tutorial series this year. Today is day 5 and we're again focusing on ARKit, but today we're going to have a look at plane detection and light estimation. So just a quick wrap up of what we did so far. First, we created a 3D model of Earth and placed it using SceneKit in a 3D world, giving it a nice star background, a nice star system. Second, yesterday we used the same Earth model and put it into 3D space, but now using augmented reality. And now part 3 of this series is going to enable us to perform plane detection and only place our Earth on a detected surface. So this would be great if you plan to place something on a table or something like that. And we are even going to perform light estimation now, so that the environmental light conditions are going to be reflected in your or on your 3D models, as you can see right here. This is going to be really cool. A quick reminder here at the beginning is about the Slack community that I have created, a Slack workspace for our community here. You can join this Slack workspace for free using the link in the video description below, and this has already become a great place for this community to actually help each other out with problems around development, a great place for starters to get their first tips and tricks. And I am also happy to actually be able to sometimes even answer your questions if I can. So this is the Slack community. Check this out in the video description below. To get started, you can just download yesterday's project, which is the 3D Earth Augmented Reality project from GitHub. You will find the link in the video description down below, and we can simply hit the clone our download button and open our project directly in Xcode, or just download the zip file with the project included. And if I now open that one up, you will see that we already have some code here in the view controller. We have our Earth node with all of the material applied to it, and the material is also saved here in our assets folder. And today we're going to focus on the view controller, because this is where all the magic for us now happens. And we're going to change some of the standard implementation that comes with the standard template for an AR SceneKit application. And we're going to start this whole thing by defining some properties. And as you know, our main goals in this tutorial is to actually detect plane surfaces where we can place our Earth on top. And this could be useful for any kind of application if you just want to place objects on a table, or you want to roll out a complete scene on a flat surface. And you can use these techniques that you're going to learn today. And also we're going to focus on light estimation, so that the object, or our Earth in that case, is going to behave accordingly when the light situation changes. And therefore we're going to add some properties right now. We're going to start with a plane geometry object, which is going to be an SCN plane object, and this is just a representation for what we add later. This could be also a box, for example, but the plane, SCN plane, doesn't really have a height that we need to define, so we can work with that. And since we also have to store the number of planes that we already have found, the different planes that we have found, we're going to create a new constant here called plane identifiers, and we're going to use an array of UUIDs for that to uniquely identify each plane that we have already created. And the next thing that we need is an array of anchors, which we simply define here. And as you can see in AR anchor, this is really a kind of magical thing, because this is a real-world position and orientation that can be used for placing objects in our augmented reality scene. So we're going to use a bunch of these anchors, because we're going to receive a bunch of them, and we're storing them in such an AR anchor array. And last but not least, we also want to work with these light estimations, and therefore we're not going to use default lighting. Instead, we're going to use our own scene light, which is going to be an object of type SCN light. So these are all the properties that we're going to need. And now we're going through each of these functions, view to load, view will appear, and so on, and change the standard implementation or the standard code that comes with an ARKit template. And we're actually, maybe we should start with view will appear, because this is where we're actually configuring our AR session. And we get this standard configuration right here, which is the AR world tracking configuration. But this is not a configuration that has plane detection enabled by default. So what we can do to change that is taking this configuration and access the plane detection property. And this is a value specifying whether and how the session attempts to automatically detect flat surfaces in a camera captured image. So this is the plane detection property, and we're going to set this to horizontal, which allows us to detect horizontal surfaces in our camera image, which is really cool, but we cannot yet display these surfaces or do anything with that. This just enables plane detection so that we get data that we can work with. And the same is true for light estimation. This is also part of the configuration for our AR session. And here what we have to do is activate light estimations with the property isLightEstimationEnabled. We set this to true to actually also get data that we can use to estimate the lighting for our objects. And these were now the first important steps here for the configuration of our AR session. And now we are going to switch to the view to load function. And here, as you can see, we set first of all the delegate to self. And this gives us the opportunity to access many of the important ARKit delegate functions that we are using right now, or in a few minutes. We're setting the statistics to true, also kind of obvious. We get all of that with the template code, but we can remove these statistics as we are moving to a production application, of course. This is just now for development. And then we have this creation of a scene, SCN scene, that we then set to our scene view in our main storyboard, in our view controller. And what I'd like to do now is, first of all, to take my scene view and like here, before we define the scene, and the scene view has something called default lighting. And I'm going to access this auto-enables default lighting property and set this to false, since we're dealing with our own light here. And after we have actually set the scene to our scene view scene property, I could think about creating now my own light. And we already have created a property for that, but now I'm going to access this property, scene light, and initialize that with an SCN light initializer. And here we can directly set the light's type, and I'd like to have an omnidirectional light, also known as a point light. And with that, I've configured the type of light that I'd like to use. And now that I have this SCN light object, I have to create a node that I can actually add to my scene. So therefore, I'm creating a light node with an SCN node, and then using the light node and set its light property to scene light. Scene light. Okay, and now all that's left to do here for our node is to actually have a position, and since we're in 3D space, I'm using an SCN vector, initializing it with an x coordinate, let's say 0 here, y10, and z position 2. Z. Let me just set the white space correctly, since we do not get auto-completion here at the moment. But now, okay, we have the position for our light node, and now we're using our scene view, of course, the scene, its root node, and we add our light node as a child node here. And this is the configuration for our AR session and for our world. We do not have to do anything more here. And now we can actually start with the interesting part that is actually related to plane detection. And if we scroll down a little after the touches began function and the did receive memory warning, we are getting a mark that here we're actually starting with the AR SCN view delegate functions. And here the first function is actually the most interesting one for us at the moment, which is renderer node for anchor. And this function is always called when we're actually finding an anchor, or when ARKit finds an anchor, and if that is the case, we are returning a new and empty node by default if this function is turned on. But we are actually adding our plane to that node. So let's first of all make this node changeable by making it a variable. And then what we can do in this function is check if we get actually a plane anchor. And as you can see, we have a parameter here called anchor. So we can take this one and check if we can cast that to an AR plane anchor. And if this conversion works and we get a plane anchor here, then what I like to do is initialize. This is the point where I actually want to initialize my node. So I'm defining that as an SCN node, and make this optional. And here I'd like to define this node first, or initialize that node with an SCN node initializer. So now that we have our node in place, we can actually create our geometry for our plane, and therefore we have already created a property that we have to access in another function later. This is why we have it as a global property for our project here. So we are starting with the plane geometry and initialize that with an SCN plane. And this is a rectangular, one-sided plane geometry of specified width and height. So we have to specify a width and height right here. And the width is now coming from our plane anchor's extend. So I have to use my plane anchor, its extend, and its x value here. And for the height, we're actually using the z coordinate, or the z extend of our plane anchor. So we're taking the plane anchor, we're using its extend and its z value. And then the last thing we have to do with both of these values is to convert that to a CG float so that the SCN plane can be initialized. So CG float around that. And now what we also have to do is to specify a material for our plane geometry. So I'm using this plane geometry, using its first material, its diffuse property. This is actually what we then see on the screen, and the contents, and I'm initializing that with a color, let's say UI color, white, white with a alpha channel, so alpha component white with alpha component, so that it's a little bit translucent. Let's set this to 0.5. And with that, we've created our plane geometry. And now using this plane geometry, we can create a plane node that we can add to our node here in this from this function that we're going to return using this delegate function. And we need to initialize our node with a geometry. So using SCN node and initialize it with our plane geometry that we've just created. And now this plane node also needs, of course, a position in our 3D space, in our augmented reality. So we are using our node, access its position, and define a SCN vector for its current position. And therefore for the x coordinate, we're using our plane anchor and its center and its x position. For the y position, we're using 0, and for the z position, we're using plane, anchor, and center, and z. And since we're using SceneKit here and using planes in SceneKit, these are vertical. So this is why we initialized our vector here with a y coordinate of 0. And also what we have to do is to rotate our node now by 90 degrees around the x-axis. So therefore, I'm using the plane node, its transform, using SCN matrix for and make a rotation of 90 degrees. So this would be pi divided by 2. And we're using a float value here, so we can use negative float axis pi and divide that by 2. We're using 1 for the x value here because we want to rotate around the x-axis, and we're using 0 and 0 for y and z. And this is now the configuration for our plane node that we can add to the node object that we have already created and add this as a child plain node. And the last step that we have to take is, since we got an anchor, our plain anchor, we should add this anchor to our list of anchors. So I'm accessing my anchors array here, and I append, not the contents of, but just append my plain anchor right now. And this is now for the first time that we find a node for a specific anchor in our augmented reality scene. But as we move along across a table or through a room, we are going to get updates, and we need to take care of these updates using the did update function here, did update node for anchor of our renderer. And what we have to do here now is to check, first of all, if we get a plain anchor again. So I'm checking with an if let statement, plain anchor equals anchor, that we have here as a parameter in the did update function. Cast that again to an AR plain anchor. It's very simple stuff here, plain anchor. Now we can check that we have that, and if we have a new plain anchor available, we should check if our anchors array already contains this this plain anchor. So I'm checking if anchors contains plain anchor. Plain anchor, of course. So now, if our list of anchors already contains the plain anchor that we have right now, then we need to check if we already have put a plain geometry, so our plain node, into this plain surface. So we're using our node that we have here as a parameter, and if this node and its child nodes and its count is not contains child nodes and its count is greater than 0, then we know that we already have a plain node in the area of this plain anchor. And then what we can do is create a plain node object and use that node and its child nodes and its first object here, because then we already have such a plane and we can change the plane's position. So now let's use that plain node, its position, and create another SCN vector with the x position of the plain anchor and its center and its x. For y, we're adding 0, and plain anchor for z, we're using plain anchor, center, and z. And now that we have that, we can change our plane's geometry. So we're creating a let statement here for a plane using the plain node. Check if we have a geometry here that we can cast to an SCN plane. And then we're updating the width and height using the plane. Its width, set it to, let's just convert that right now, to a plain anchor. Plain anchor, its new extend, or its extend that we get here, and its x value, and the same thing, plain for the height, CG float, the plain anchor, and its extend, and its z value. And now with that, we can actually update the detected surface or the detected area of our from our augmented reality scene, but we still need to update our materials, or to update the plane materials dimension. As you can see, we've set the material right here, but the dimensions do not yet update, since we're only updating the geometry right here and not the material. And therefore, we're going to add a new function right below the did update function here from the renderer. I'm going to call that update material. And in this function, we are first of all going to get the material from our plane geometry. So let material equals self. We can use the plane geometry here because this is a global property. Access the materials, and first to get the material that we want to work with, and then we can use the material, its diffuse, and we can transform the content here using contents transform, this property, and then we can simply make a scale here using a matrix, scn matrix for make scale operation, and we need to actually scale that with the plane geometries width and height. So we're using a float value here, since this requires us to put in float values using self plane geometry and its width. And let's do the same for the height. So for sy here, for the y scale. So again, we're needing a float here, self plane geometry and height, and simply 1 for z here for the z scale. And that is actually all there is to updating the material. Now we still need to call that at 2 positions. First of all, we need to call it here when we indeed do the updates as we move along or across a room or along a surface. So I'm calling update material right here. And I'm doing the same thing before we're actually adding our plane node for the first time, so that when we set the position and the transform of our plane node together with its geometry, we also want to update the material right there. And at this point, I would recommend to test this, and you should be able to use a real device now and actually be able to detect any surface or flat surface in your room or in your environment right now. And this should also have a visual representation through your camera's viewfinder at the moment. But now we also would like to be able to actually touch only this surface and add an object or a node to the exact position you are touching, but only if it is on top of a detected surface. And therefore, we're going to add another function so that we can indeed do that. And the function that we're going to use or call is add node at location, with a location as a CG point. And this function is supposed to check if we already have anchors in place that we can use. And if we already have anchors, we want to clone a node and add it to the anchor at the specified location that you've actually touched on your device's surface. So first of all, let's create a guard statement here for the anchors. And if we have more anchors than 0, then everything is fine, we can continue. But else, we can, for example, print a message and say anchors are not created yet, and simply return here from this function, because then we cannot really continue. But if we have anchors in place, and this is why we actually have this array of anchors, then we can actually perform a hit test. So we're firing a ray through your finger. Imagine your finger actually shoots a ray of light through your surface of your screen directly into the real world. And this is what we're doing when we're performing a hit test. So we're creating a hit results object here using the scene view and calling hit test at a specific point. This is the location that we have specified here as a parameter. And the types that we're interested in are existing plane using extend. So by using the extend, we're also able to actually touch a surface where, or touch an area where our visual representation of a detected plane has not yet reached. So we can use the extend here as well. And also we could just use the existing plane that we really discovered already. But now we're using the plane using its extend. And by performing this hit test, we can now check if we have hit results. So if the hit results and its count are greater than 0, then we can continue and create a results object here with or a result object, because we are only interested in one result actually, using hit results and the first object right here. And then we can get a location from this result, because we are interested in the location in 3D space where we actually want to position our Earth. And therefore, we're creating a new location right here. So we are creating a new vector, scn vector 3. And for x, we're using the result. and its world transform. And this is the, as you can see here, the position and orientation of the hit test result relative to the world coordinate system. Now, at the moment, since we have this world transform, this is a matrix, a 4x4 matrix, and we get the position in the fourth column here. So since we're starting to count at 0, we have to use 3 here for the fourth column, and accessing x for our x position in 3D space. Then we want to get the y position. So again, using the result, world transform, the columns 3, y, and since I want to hover our Earth a little bit about the surface, I'm adding 15 centimeters here, so 0.15 to our y value. And for the z position, here y is missing, so y, and for the z, we will just use again the result, world transform, columns 3 and z. So this gives us the location where we actually want to position our Earth, and just as we did in the last two tutorials, we're creating an Earth node, initialize that with Earth node, and setting Earth node's position to the new position, or to the new location actually, and then we're good to go. There is one error still because we did not access columns here. So columns 3x and so on. And now we have set the position. We can use our scene view, its scene, its root node, and add our Earth as a child node. So that's all there is to it. Now, the last question actually is, how do we really add this? How do we reconfigure the touches begin function? So let's find touches begin real quickly. And indeed, we can delete a lot of the code that we have written in the touches begin function. As a matter of fact, we only keep the first 2 lines where we get the touches from the touches set. And from one of the touches, the first touch, we're getting the location in our scene view, and now all we need to do is call add node, add location, pass along the location, and we're done. And you could test this now again and see if you can indeed place an Earth node at a specific location on a plane surface. Let me just quickly unwrap this right here, and we should be good to go. Now, the last step that I want to take with you now is, as I promised, light estimation. We already activated this light estimation feature, but we cannot yet, or our objects do not yet adapt to the light. So therefore, we're going to add another delegate function. I'm going to do that maybe before we are adding, or before we're adding nodes, or where we're performing node for anchor. Here I'm going to add the update at time function of the renderer. And as you can see here, this is giving us a renderer and a time that we do not really need, but this is a place where we can continuously do or perform updates. And what I'd like to update is actually the intensity of our scene light that we've defined as a property earlier. So first of all, I'm defining an if-let statement here with to check if we actually get an estimate for our light using self, scene view, the session, the current frame, and its light estimate. And if we get such a light estimate, I'm using the scene light, the intensity, and set this intensity to the estimate and its ambient intensity. And this allows us to actually change the lighting effects on our 3D or Earth object, because we can, of course, add multiple objects. And this is going to reflect the ambient intensity, or the measured ambient intensity of the light on the 3D objects that we put into our augmented reality scene. And if everything went according to plan, then you should now be able to actually detect surfaces, place an object only on top of a detected surface, but also if you turn down the light, you should be able to see the changes in light environment reflected on our 3D object. First, we create an Earth. Second, we placed Earth in into augmented reality, and now we have even improved that furthermore with plane detection and light estimation. If you like the video so far, give it a thumbs up. Make sure to subscribe to this channel to not miss any of the 24 days of Swift tutorials this year. And tomorrow there won't be a video, but the day after tomorrow we are going to continue the series as promised. So thank you so much for watching, and I'll see you in the next one.